I'm looking for something to give us a visual. So this was the only clock I could find I could get a picture of. Let's say that the second hand of a clock, is 10.2 centimeters. So how does that relate to the circle? If it's the second hand of the clock, would that be the radius that we might want to use?
Yes.
Okay. So the second hand of the clock is 10.2 centimeters. We want to find the linear speed as it passes around the face of the clock. Okay, in other words, say this is the second hand. We want the linear speed as it goes all the way around the face of the clock.
But don't we need the angular speed?
So in order to get that, we need the angular speed, don't we? You're exactly right. So can we find the angular speed? What is one complete revolution?
360.
But we're in 2 pi. All right, so we know that the intercepted arc is going to be 2 pi. And did we say that, so is that that's the intercepted arc. How long does it take me to go that all the way around?
24 hours.
No, second hand. It takes 60 seconds for it to go all the way around, doesn't it? So if it's speed, it's 2 pi over 60 seconds times the radius. Remember, speed is always related to time. And it takes 60 seconds for that second hand to go all the way around. If it was a minute hand, how long would it take a minute hand to go all the way around? 60 minutes to go all the way around the face of the clock. All right, so here, this is approximately, let's see. So you can plug that in the calculator and you can get an approximation.
I can do that.
So if it ever has like a decimal, would you just want us to plug it in?
Mm-hmm.
I got 1.07.
Okay, 1.07, 1.068. Okay, and what was the unit of measure? Centimeters. And since we're talking linear speed, centimeters per second.
So you did you like,
One revolution,
yes, okay,
and it takes 60 seconds to do that one revolution. This is my
Yes.
angular speed.
okay.
If all I ask you for angular speed, it would be pi over 30. Okay, or you could get a decimal approximation.
And so did
And
you
then
just
to
like
get-
reduce the 60 and the 10.2? Or how did
He just multiplied it on the calculator.
Oh, okay.
Okay, so to get linear, this is angular speed. 2 pi over 60 is angular speed. Linear speed, we simply multiply it by the radius, which was 10.2 centimeters.
And just kind of fill in each thing.
Mm-hmm. So let's think of another one. Same kind of example. Let me see. I can't move it.
Whoa.
Well, we'll just move the clock down. Okay, so let's look at a different clock. This time, the second hand is 8 centimeters. Find the linear speed here as it passes around the face of the clock. So 8 centimeters. What's the formula for linear speed?
W times R.
R times omega, or omega times R. What is our angular speed?
60.
What's the cut, what's the central angle?
2 pi.
2 pi. And how long does it take to go 2 pi? 60 seconds. And our radius is 8. And so we get 16 pi over 60.
Which is approximately 0.838.
Okay, so 0.838 centimeters per second would be the linear speed. Hallelujah. Okay, let's look at a couple of different problems. All right, we've got a wind turbine out where it's real windy because you're trying to generate electricity. And the blades of the wind turbine, the blades of a turbine are 116 feet.
How long are the blades of the wind turbine?
In this one, they're 116 feet. Of course, you know that wind turbines kill an awful lot of birds.
Yeah.
So, kind of one of those mixed blessings. And the propeller,
Stupid birds.
the propeller rotates at 15 revolutions per minute. RPM, revolutions per minute. How much is each revolution? 2 pi. All the way around is 2 pi. So my angular speed is going to be 2 pi, because that's one revolution, but how many revolutions do we have? 15. So 2 pi times 15, and this was per minute. So angular speed is 30 pi. 30 pi radians per minute. How do we get linear speed? We multiply that by 30 pi times 116. This was feet per minute. And so we get, what, 3480 pi? You've got a calculator handy. I don't have one up here.
32 points. I got a big number, like 10,900.
I got 3480.
Oh.
Oh, wait, no, never mind. I didn't do 5.
10,933. 10,932 point. Okay, so I'm going to round it up. Okay, so this is 10,933 feet per minute. Not bad?
Not bad at all.
See, these are not bad. They're not bad problems. Just because you see applications doesn't mean they have to be hard. Especially when you have the formulas right there on the board.
Squad.
This is like physics.
Yeah, it is. And you have to use math and physics.
Yeah.
Pretty sure.
So,
Oh,
are you taking physics this year?
No, man, I'm in chemistry.
Well, you have to use math and chemistry as well.
It's terrible.
So let's do another one similar. We have circular blade, and let's see. Okay, we have a circular blade on a saw, circular saw. And the blade rotates at 2,400 revolutions per minute. Let's see if we can find the angular speed. What is the angular speed?
it's moving pretty fast.
Moving pretty fast. That's why you don't want to get your fingers in there. They're gone before you know it.
Very good.
How do we find angular speed, Robert?
It's this weird W equals the central angle over time.
Okay, so what's our central angle going to be?
For which one?
For this circular saw that rotates at 20, that moves at 2,400 RPM.
24.
1 revolution is 2400. What's the angle for 1 revolution?
360.
2 pi.
2 pi.
No, 2 pi.
So it's 2400 times 2 pi. So how many, what's the central angle? Or the angular speed?
4,800.
4,800 pi radians per minute. Now this is radians. Remember, we have to use radian measure to use these formulas. We can't use degrees. Now, if this saw has a radius of 4 inches, how do I get linear speed? Multiply our angular speed by 4. 4 times. Okay, and what is that?
60,318.5 seconds.
Okay. So I'm going to keep it in pi for right now. That's going to be 32. Did I do that right? Okay, this is revolutions per minute. What if I wanted to get revolutions per second? How would I change that? If we divide by 60, let's see what we get. This should be 19. Okay, if we change to per second, we can divide by 60.
320.
And we get about 320 pi inches per minute, or inches per second, or you could even get a decimal approximation. Okay, so those are not hard, are they? Find your central angle, and then you can find linear speed by multiplying by the radius. One more quick example, or one different formula, is the area of a sector of a circle. An example of this would be, you've seen those sprinklers, that one side stays the same and the other one's going like this? Yeah. Okay, it cuts out. We can use the formula for an area of a sector of a circle to see how much area you're watering. Area of a sector of a circle. If we go back to our geometry days, here's our circle. I don't have my little circle maker up here. I can't use it with this. But the area of a sector of a circle is the area cut out between 2 radii of the circle. The area of the sector of a circle would be this part, between the 2 radius. And the formula for the area of a sector of a circle is area equals 1/2 r squared theta. So I didn't get I'll put that formula on the board, but I forgot to put it up there before y'all got here. 1/2 r squared theta. And theta is the central angle. And what do you think we have to specify about the central angle? It has to be in radian measure. In radian measure. All right, so you got a sprinkler on a golf course, and it sprays over a distance of 70 feet, and it rotates through an angle of 120 degrees. Okay, so if it sprays 70 feet, that's going to be the radius of our circle, right? Because it's going to go from here,
It's gonna go, it's not gonna.
120 degrees would be about like that. So it's going to go like this and back. So if we want to find the area that it sprays, how much grass on the fairway is going to actually get water? What do we have to do first? Change our angle to radians. How do we do that?
2 pi over 3. Oh, yeah, pi over line.
Multiply 120 degrees times pi over 180 degrees. So the zeros cancel, and 6 goes both times. So our central angle is 2 pi over 3. So we take our formula. Area is 1/2 times the radius squared times 2 pi over 3. All right, we know those 2's cancel. So 70 squared is 4,900 pi over 3, and I cannot, that doesn't divide evenly. If you multiply it out, what do you get?
5,131.3.
Okay, approximately 5,131 square feet is the area that is watered. Okay, so those are the application problems for this section. So on page 290, '90 through 92, 94 through 96, 98 through 100, and 102 through 104. At a Ferris wheel. And say you're sitting here on the Ferris wheel. You are moving, as that Ferris wheel moves, you're moving along a circular path, right? It may take forever, because it seems like Ferris wheel rides are very, very slow, but you're moving along a circular path. And so we can find your linear speed, or how fast you're moving around the, could we say that's a circumference of the circle? It's a circular path, so we could find how fast you're moving, and we call that linear speed. In our example, the linear speed is how fast you're moving around the Ferris wheel. So linear speed is how fast a particle, a person, a point, we'll just be generic and say a particle moves around a circular path. So when you're thinking linear speed, we're really thinking circumference. What's happening on the outside? Angular speed is how fast the angle changes. And we're going to look at angular speed first, but how fast the angle changes. And I misspelled that. For instance, let's say you can sort of see these spokes on the Ferris wheel. Say, if this were this, I can't tell it. Maybe that's the Ferris wheel right here. The spoke goes out here, and you're moving at one speed around here, but this is going through an angle. As you move, this whole thing it sweeps out a central angle. Can you see that? So angular speed has to do with that angle, how fast the angle's moving. Speed just relates it to time. So linear speed would be your distance around over time. Angular speed would be the change in, or the rotation over time. So we're going to look at those two things, linear speed and angular speed. And I've already written formulas on the board. I'll keep those formulas up. I'm not going to ask you to memorize those formulas. I will leave those up. My other class would have liked for me to have done that when we did this, but I didn't. But I'll leave it up for you guys. All right, so let's think about angular speed. We're going to start with that. And in your book, angular speed is denoted with the Greek letter omega. Kind of a weird looking W. That's your angular speed. And angular speed is the central angle over time. Or we could say theta over time. That would give us our angular speed. So, what is, if we went all the way around the circle, what's the central angle that was cut out? 360, but we're doing, what did we say we have to be in? Radians. What is 360 degrees? How does that convert to radian measure? 2 pi. So one complete revolution is always 2 pi. So ever how much of an angle you went through, in this case, if you start here on the Ferris wheel and we take a complete rotation, we've just gone 2 pi over however long it takes. Probably it might take a couple of minutes or more to go all the way, depending on if they're loading or unloading. That's why I don't like to ride the Ferris wheel. If you could just ride the Ferris wheel and not have to stop so much, it'd be fine. But it takes too long to get everybody on and then get everybody off. All right, so angular speed is our central angle over time. It always has to be in radian measure. Radian measure. Now to find linear speed, they use a funny looking V, and that is equal to the radius times the angular speed. We could think of it as the intercepted arc over time, however much you cut out of that the arc length over time. But when we're actually calculating it, this is going to be the formula you want to use. The radius times the angular speed gives us linear speed. Remember, angular speed always has to be in radian measure. Right? Formulas are on the board. Let me make a note. Theta must be in radians.
So why do you have the function b equal to s over 2?
Okay, this is linear speed. Remember, it's intercepted arc over time, but for calculating it is very often, most of the time, we're going to be using the radius times the angular speed.
So we really only need to know the bottom equation?
Yes. We could go through the process of how we get from one to the other, but I think probably to be less confusing, just give you the formulas. Sound okay? All right, let's look at intercepted arc is equal to theta times the radius from the previous formula, and theta always has to be in radian measure. So if we're going to use this formula, even if you're given an angle in degrees, you've got to convert it to radian measure. So theta is always in radian measure. All right, so let's think about if we have a circle that has a radius of 4 inches. Let me write out radius so you won't think it's radians. The radius is 4 inches, and I want to find S, the length of the intercepted arc, if it's intercepted by a central angle of 240 degrees. Okay, what did we say first we have to do? What did we say about that central angle?
To make it radian?
It has to be in radian measure. We can't use degrees. So on these formulas that we're working with today, we always have to be sure that if we're given an angle in degrees, we convert it to radian measure. And how do we convert to radian measure?
180 over pi? Or is it pi 180?
What are we trying to get rid of? Degrees, so that means the degrees have to go on bottom.
Pi over.
Okay. So if we simplify this, notice easy way to do it, the zeros cancel, and then I'm just looking at 24/18, and 6 goes into both of those, so that becomes 4 pi over 3. Okay, so if I want to find the length of the intercepted arc, now we just take theta, which we just found in radian measure, was 4 pi over 3. And we're going to multiply that by 4 inches. So the intercepted arc is going to be 16 pi over 3 inches. Pretty easy? Okay, what about a circle that has a radius of 27 inches? And we want to find the length of the arc that's intercepted by a central angle pi, no, let's say 160 degrees. What's first step, Annalisa?
Set up
To do what? Why do I set up a fraction?
to find the degree.
I already have degrees. What am I trying to change it to? Robert,
What?
this is not the time to get that out. You need to be taking notes for today's class. What do I need to do with that 160 degrees?
Multiply.
Why?
So you can get it's called, so you can get it pi for
Pi form, which is what kind of angle? What kind of measure, Zach?
Radian?
Radians. I want to change it to radians. So that means we're going to do 160 degrees times pi over 180 degrees. So 2 goes into 16 8 times,
8 pi over 9.
and we get 8 pi over 9. So if I want to find the measure of the central angle, we S equals 27, the radius times the central angle, and 8 times 7 is 54,
Could you cancel
16.
it? Yeah, could you cancel 27 and 9?
Yes, thank you. That would have been so much easier.
Can you times it?
Yes, so I did something wrong. Yes, thank you. That would be, yes.
So I times them, I multiplied them, and then like I got 216 over pi over 9, then I reduced there. Would that be?
You can do that. Okay. That's what I was doing, except I multiplied wrong. So 24 pi. All right, and you could, if you wanted a decimal approximation, you could just plug in 24 pi into your calculator. Okay, so anytime that you're looking for arc length, the first thing you have to make sure of is what about your angle? Andrew? What's significant about the angle that you're using? What do you have to make sure of?
I don't know.
Addie?
well, it has to be a central angle,
It has to be a central angle.
and it has to be in degrees or radians.
Radian measure. It has to be in radian measure. So if you're given an angle in degrees, you have to change it to radian measure. All right. So we said that our intercepted arc is S equals R times theta. That's what we've been working with. And this can help us also analyze motion of a particle that's moving along a circular path. For instance, if we look